Alright, today we're going to have a look at solving equations involving different trigonometric functions, or single equations involving different trigonometric functions. Okay, so how do we solve questions like this? We can see in the first example below that we've got two different trigonometric functions in our question. And we can see in, say, this question here, we've got two different angles, 2x and x. The only way at the moment that we can solve these is by getting our either angles or functions to be the same, and sometimes it needs to be both. So we must somehow manipulate our formula to get an expression involving one trigonometric function and also the exact same angle. Okay, so let's have a go at solving this. Solve the equation 2 tan of theta is equal to sec of theta. Right, and we're in the domain from 0 to 360 degrees. We can see here we've got two different functions. We've got tan of theta and sec of theta. The way we're going to fix that is by making tan of theta sine on cos. So this is 2 times sine theta on cosine of theta. And that's equal to 1 on cos of theta, because sec is 1 over cos. We can see now that those two will cancel, and we've got sine theta divided by 2 is equal to a half. If we take the sine inverse of both sides, of course we get theta is 30 degrees or 150 degrees. Now there is an alternate way of solving this question, and it's by squaring both sides. If you do that, you'll get one of the identities. I think sec theta is 1 plus tan squared theta, and you can use that, but personally I prefer doing it this way. Okay, we're going to solve sine of 2x is equal to sine of x. Now I'm going to show you an incorrect way of solving this problem, and then we're going to fix that by doing it correctly. And that's why I've got a little trap thing down there. So we know first up that when we're solving these, we have to get it in terms of the same function and the same angle. Here we need to fix that angle there because I've got a 2x and an x. We know that sine of 2x is 2 sine x cos x. And this is equal to sine of x. The problem with this is that you might think, okay, I'm going to do that and cancel them from both sides. We actually can't do that in this question. The reason we can't do that is because if you cancel sine x from both sides, and that's the trap in this question, you're going to miss out on one of the solutions. So when you have two things that are equally one on each side of the equation, not on the bottom of a fraction, but literally just on either side of the equation, we can't cancel them. You must do this. We're going to say 2 sine x cos x minus sine of x equals 0, and then we're going to factorize. Because of that, if we made that mistake, if we did that trap, we're going to miss out on this solution here. Sine of x is equal to 0. We would only get cosine of x is equal to a half. Now sine of x is equal to 0 at 0 and pi, and cosine of x is equal to a half. What is that at pi on 3 and 5 pi on 3. Okay, next question here, we've got solving sine of theta plus pi on 6 is equal to 2 sine of theta minus pi on 6. We can see with these questions it's starting to utilize all of the knowledge that we've learnt in year 11 in terms of our advanced trigonometric knowledge and our extension 1 trig knowledge. And this first exercise in the Cambridge textbook really is just going to smash you with all of that content all in one in terms of our equations. Again, we've got different angles here, so we need to try and simplify that. And what we're going to do first is by expanding these using the compound angle formula. So the left-hand side is going to be sine of theta times cosine of pi on 6 plus sine of pi on 6 times by cos of theta. And that's going to be equal to 2 times by sine of theta cos of pi on 6 minus sine of pi on 6 cos of theta. Okay. Now, we might want to find out what cos of pi on 6 and sine of pi on 6 is, and etc., and do some expanding. I'm going to not do that in this example because I think it's just going to make our work a lot harder. So let's not find out what they are, and let's just expand this for the moment. So we've got sine of theta cos of pi on 6 plus sine of pi on 6 cos of theta, and that's equal to 2 sine of theta cos of pi on 6 minus 2 sine of pi on 6 cos of theta. Now we can see in this expression that sine of theta cos of pi on 6 is exactly what we see here, and this is exactly what we see here. So what we're going to do is plus this to the other side and minus this to the other side. So we're going to get 3 sine of pi on 6 cos of theta is equal to sine of theta cos of pi on 6. Now, sine of pi on 6 is a half, so this is going to be 3 on 2 cos theta, and cos of pi on 6 is root 3 on 2, so root 3 on 2 sine theta. Now, obviously, those 2's on the bottom will die, and we're going to get 3 cosine of theta is equal to root 3 sine of theta, which means tan of theta, by dividing the cos over, is root 3 on 3, or 3 on root 3? Yeah, 3 on root 3, which is root 3. If we take the tan inverse of both sides, tan inverse of root 3 is pi on 3, and then of course in the third quadrant that will give us a related angle of 4 pi on 3. Okay, next one. This question's interesting because it involves a quite basic property of sine squared x plus cos squared of x being 1, but it's not something that you might have initially thought to do. So let's expand first up the left-hand side. We know sine of 2x is 2 sine x cos x. And we know cos of 2x is cos squared x minus sine squared x. And that's going to be equal to sine squared x. Now, that plus 1, it's really going to make trouble for us because I don't have any numbers anywhere else in my expression. I've only got sine squared x and cos squared x and 2 and cos. So I don't really have any numbers on their own. So let's get rid of that number on its own and say it's equal to sine squared x plus cos squared x. And that's a strategy that sometimes can be useful. Because of that, we can simplify all of that and say that this is equal to 3 sine squared of x. That's by plussing this over to the other side, so 1, 2, 3. And then we've got the cos squared x look like they'll die. That dies and that dies. And then we can minus this over to the other side. So 3 sine squared of x minus 2 sine of x cos of x. And that's going to be equal, of course, to 0. Okay. Now again, it's not looking too good. The only thing I can think of doing at the moment is factorizing out a sine of x. So let's go sine of x. And we're going to have, 3 sine of x minus 2 cos of x. And that's equal to 0. Okay. That potentially will work. Let's have a go at doing that. So we're going to get sine of x is equal to 0. And we're also going to get 3 sine of x. Pen's not being the best. 3 sine of x minus 2 cos of x equals 0. And if we did some simplifying, that will give us, first up, 3 sine of x is equal to 2 cos of x. which means that tan of x is 2 on 3. Okay, so we've got two expressions there. We know that sine of x is equal to 0 at 0, pi, and 2 pi. And tan of x is not quite, equaling 2 on 3 is not quite as exact. Let me just quickly put my calculator in radians. So tan inverse of 2 on 3 is 0.588. And then since tan is also positive in the third quadrant, our second expression, our second angle is going to be pi plus 0.588, which is plus pi, we get 3.72. 3.73 actually. Alright, and those are our answers there. So when we're solving these trig equations, don't be fooled, they're not always going to be exact answers. Sometimes they are, but we can see here we've got two kind of like normal answers and then two decimals. Okay, I think this next one's a long one. So we're going to have a go at solving sine of 3x plus sine of 2x is sine of x. To do this problem, we're going to realize that sine of 3x is actually sine of 2x plus x. So sine of 2x plus x. Now sine of 2x plus x, expanding that compound angle, we get sine of 2x cos of x plus sine of x cos of 2x. If we keep going expanding that, sine of 2x is 2 sine x cos x, so this will be 2 sine x cos squared of x. We times through that cos. And cos of 2x is cos squared x minus sine squared x. So if we expand through that sine x, it's going to be cos squared x sine x minus sine cubed of x. Now cos squared of x is 1 minus sine squared of x, so this is going to be 2 sine of x minus 2 sine cubed of x, plus cos squared of x again is 1 minus sine squared x, so this is going to be sine x minus sine cubed of x, expanding through that sine of x, minus sine cubed of x. Simplifying that, we get that this is equal to 3 sine of x, 2 plus 1 is 3 sine of x, minus 2 minus 1 minus 1 is minus 4 sine cubed of x. Look, now personally I would have gone from here straight to here, but if you want more or less steps on what I've done, that's completely fine. So 3 sine of x minus 4 sine cubed of x. Plugging that back into our original equation, so putting that back up to here, we're going to have this is equal to 3 sine of x minus 4 sine cubed of x, plus sine of 2x is 2 sine x cos x, and that's equal to sine of x. Okay. Now we can have a go at simplifying this. So let's say this is equal to, let's plus everything over to the right hand side, 4 sine cubed of x minus 2 sine of x cos of x, and that's going to be 1 minus 3 is minus 2 sine of x, and that's equal to 0. Okay. Now it looks like we can take out a factor of 2 sine of x. Let's do that. 2 sine of x, 2 sine squared x minus cos x minus 1 equals 0. So one solution is 2 sine of x is equal to 0. And our other one is sine squared x minus cos x minus 1 equals 0. Now, sine squared of x is 1 minus cos squared of x. So this is 2 minus 2 cos squared of x minus cos of x minus 1 equals 0. And that actually ends up being the quadratic if we plus everything to the other side. 2 cos squared of x plus cos x minus 1. Now if we apply the quadratic formula here, we're going to get cos of x is equal to b minus b, which is minus 1, plus or minus the square root of 1 squared minus 4 times 2 times minus 1, which is 9, on 2 times 2 is 4. Now that means cos of x is equal to a half, or minus 1. So therefore our solutions are x is equal to, when sine of x is 0, which is 0 and pi, then when sine of a cos of x is equal to a half, which is at pi on 3 and 5 pi on 3, and then also when cos of x is equal to minus 1, which is at pi, which we've already got that solution over there. That was a long one, but fun. Okay, number 6, we've got 3 cos x squared of alpha is equal to 4 cot of alpha. Right, here we can see that we've got 2 different functions, but there isn't a unique rule that relates cosec and cot, and that's the fact that cosec squared of alpha is 1 plus cot squared. So this is equal to root 3 cosec squared. Cosec squared of alpha would be root 3 plus root 3 cot squared of alpha, and that's equal to 4 cot alpha. Subtracting all of that over, we're going to get root 3 cot squared alpha minus 4 cot alpha plus root 3 equals 0. Then we can use the quadratic formula and we get cot alpha is equal to minus b, which is minus 4, which is 4, plus or minus the square root of 4 squared minus 4 times root 3 times root 3, which is 4, square root of 4, over 2a, which is 2 root 3. Now we've got cot alpha is equal to that. Now cot alpha doesn't really help us, but I know if I flip cot alpha upside down, I get tan alpha. So we can also split the other side upside down and get 2 root 3 over 4 plus or minus the square root of 4, which is 2. So that would give our 2 solutions of root 3 on 3 and root 3. So the solutions to this equation are tan alpha is equal to root 3 on 3, or 1 on root 3, or tan alpha equals root 3. Take the tan inverse of both sides and we get pi on 6, 7 pi on 6, pi on 3, and 4 pi on 3. Awesome. Okay, last couple. This one says we've got cos of 2x is equal to 4 sine squared of x minus 14 cos squared of x. Again, we've got lots of different functions and different angles. The thing that comes to mind first is the fact that cos of 2x is cos squared of x minus sine squared of x. And that's equal to 4 sine squared of x minus 14 cos squared of x. Now, I'm thinking, okay, I've got everything is sine squared or cos squared, and I know if I divide sine squared x by cos squared of x, I get tan squared of x. So let's put all the sines on the left-hand side, and all of the cosines on the right-hand side. So if I do that, I'm going to get 15 cos squared of x is equal to 5 sine squared of x, which means that tan squared of x is equal to 15 divided by 5, which is 3. We square root both sides, we get tan of x is equal to the square root of 3, but we've actually got plus or minus, because if you square root a number, remember you get its positive and its negative answer. So that means tan of x, well in the first quadrant we get pi on 3, And since we're in all 4 quadrants, we're going to get 4 answers, 1 in each quadrant. So 2 pi on 3, in the third quadrant it's 5 pi on 3, and in the fourth quadrant it's 4 pi on 3. Right. Okay, now to one that's just from the textbook. Quite a long one, this question, but anyway, we'll have a go. If tan of x is if t is equal to tan of x, show that tan of 4x is that there. Okay, let's get tan of 4x, and we're going to use our double angle identity and realize that this is 2 tan of 2x over 1 minus tan of 2x squared. That's because tan of 2x is 2 tan of x on 1 minus tan squared of x. So tan of 4x would be the same thing, except in the brackets we've now got 4 divided by 2, which is now 2. Now if t is tan of x, and we've got a 2 here, well, that means tan of x is using our half angle formula, because an angle of x is half of 2x. So we can actually use our t formula here. The t formula for tan is 2 times by 2t on 1 minus t squared. So I've substituted in the t formula for tan here, over 1 minus the t formula for tan squared, 2t on 1 minus t squared squared. Okay, we have a go at simplifying that. On the top, we're going to have 4t on 1 minus t squared. And on the bottom, I'm going to have, if we make that a common denominator, it's going to be 1 minus t squared squared minus 2t over 1 minus t squared squared. Okay, hopefully we can see that that will die with one of those, and then this will be sent to the top. So we're going to have 4t 1 minus t squared over 1 minus t squared squared minus 2t. Now if we simplify the bottom, we're going to get, or on the top first up, we've still got 4t 1 minus t squared, and the bottom, if we expand that and then simplify, we get 1 minus 6t squared plus t to the power of 4, which is what we're after. Awesome. Okay, now just for those, you're welcome to do more steps than what I've done. Personally, I would go from here, probably straight down to there. But since it is a proof, it's probably best to show all of these steps. If it wasn't a proof and you just were deriving something, then you don't have to show all of those steps. Okay, if tan of 4x tan of x is equal to 1, show that 5t to the power of 4 minus 10t squared plus 1 is equal to 0. Okay, now we're told first up that tan of x is equal to t, and we know that tan of 4x is equal to this expression. So really what the question is telling us is that I'm getting this expression, multiplying it by t, which is tan of x, and making it equal to 1. So we're getting 4t 1 minus t squared over 1 minus 6t squared plus t to the power of 4, and we're timesing that by t, or tan of x, and making it equal to 1. So on the top, we've got 4t squared 1 minus t squared, and then we're bringing this up to here, so 1 minus 6t squared plus t to the power of 4. So this t, if we couldn't see, has been multiplied by that t there, and it's become 4t squared. Now if we expand that, we're going to have 4t squared minus 4t to the power of 4 is equal to 1 minus 6t squared plus t to the power of 4. Adding everything to that side, we've got 5t to the power of 4 minus 10t squared plus 1 is equal to 0, which I'm pretty sure is what we're asked to prove. Okay. I'm not going to show in this video part C. I'm hoping that we already know how to do that, and if not, I want you to have a go on your own of proving part C. We're going to skip to part D now. Okay, hence show that pi on 10 and 3 pi on 10 satisfy those conditions there. Now, using the identity that we have just proven, or you would have proven in part C, is that first of all, tan of 4x, tan of x, well, that's going to be equal to a half of, well, first up it's going to be sine of 4x on sine of x over cos of 4x cos of x. Now, using the identity that we've derived in part C, that will tell us that this is equal to sine, or a half of, I think it's cos, yep, cos of 3x minus cos of, plus together, 5x over a half of cos of 3x plus cos of 5x. Now those halves will cancel, and we're asked to solve it when this is equal to 1. So we're making this equal to 1. So really we've got cos of 3x minus cos of 5x timesing up the denominator is equal to cos of 3x plus cos of 5x. Now we can see our cos of 3x's will die, and we're going to have 2 cos of 5x is equal to 0. Which means that cos of 5x is equal to 0. And that means 5x is whenever cos of 5x is equal to 0. Now cos inverse of 0 is pi on 2, 3 pi on 2 and so on. Dividing both sides by 5, we get x is equal to pi on 10 and 3 pi on 10, which is the two things we had to prove satisfied the equation, so we're done. Okay, last question says we have to write down the 4 real roots of this polynomial equation. Now this polynomial equation we can see is exactly the same as this polynomial equation here, except we've got x's instead of t's. Now we've shown that this polynomial equation is the same as this equation here. And we've just proven that 2 of the roots of this equation are tan of pi on 10 and tan of 3 pi on 10. However, due to the rule that tan of minus x is equal to minus tan of x, due to that rule there, we can say that tan of minus tan of pi on 10 and minus tan of 3 pi on 10 are also solutions, because if I have my equation tan of 4x, tan of x is equal to 1, if I put in my negative solutions, the two negatives will multiply and make a positive, so they'll end up just still going to be the same as these two substituted in there. So your 4 solutions are the 2 positive solutions, and since 2 negatives make a positive, it's also those two solutions there. Alright, that makes sense, thank you.